circuits, automated reasoning, logic and finite model theory, and few more things, I think. The talk will be on the fundamental synthesis. Supratik has, received more, including the Fellow of Asia Pacific Artificial Intelligence Award, Faculty Award, the Distinguished Apollos Award, the Distinguished Member of ACM, and many, many more. I'm not going to list all of them. He is also been in many, okay, I think I should stop. He's also been part of many IATS bodies and ACM bodies, and his service to the community has been very wide. We're happy to have him to start proceedings of the evening, and we started a little bit late, so I'll appropriately give you a little bit.
Okay, good. Yeah, that's important. Okay, yeah, thanks Akshay for the introduction. And I'm really thankful to the organizers for inviting me here to give this talk. It's a wonderful location celebrating Meena and her achievements. So right at the outset, I mean, my talk has got very little overlap with either complexity or algebraic computation or proof theory. So, but since Meena did seem interested in this work, I hope she'll enjoy the talk, and I hope the rest of you will enjoy the talk. So I'm going to talk about some work that we have been doing for the last close to 10 years now, Akshay being a partner in crime, and several others, some of them may be already here. So yeah, just at the outset, this is work done with Akshay, of course, who's here, and several students and colleagues, Jatin, Aman, Dror, Shubham, Sahil, Sumit, Divya, Pri, Shetal, Krishna, my colleague, Lucas, Moshe Vardi, and also a result of many fruitful discussions with Kuldeep, Mate, Priyanka, and Shubhajit. So this is kind of the setting. It's a typical computer engineer's day at work. Either a client or the engineer's boss has asked her to design a program or a circuit which takes two inputs, x1 and x2, and gives an output y. And the specification of the system could be given by, let's say, by a set of examples, or maybe by a logical formula, or maybe, these days with ChatGPT being in vogue and cousins being in vogue, so maybe it's given in natural language. And this poor person is supposed to design a system which works like this. Okay, so after some thinking and some trial and error, maybe the engineer comes up with a program like this, and whatever, does verification, testing, whatever reasoning, and figures out that yes, this is what works. And then a colleague comes and says that, well, how do you know that this program is really correct for all inputs? And more importantly, I want to change the specification a little bit, so you have to go through this entire process all over again and come up with another program. So this is, something that the engineer wishes, that if there was an algorithm which could synthesize the required program or circuit and provably correctly, then it would be nice. So you could give whatever specifications you want, and then this would go into the algorithm, and output come this provably correct system with some kind of proof of correctness of the system. Okay, so it would be nice if there was such an algorithm. And if the spec changes, there's absolutely no problem. You feed in the new spec into the algorithm, and out will come, maybe the same system works for the change spec, or maybe a different system works, but whatever comes out is once again provably correct for the specification. And so the focus of my talk today would be what is necessary or what is needed to come up with such an algorithm. And in particular, I'm going to look at specifications given by logical formulas. There is, of course, work in the literature on specifications given by examples, specifications in natural language. We will not get into that in this talk. Okay, so this is the overall setting. we are going to be given a specification as a logical formula, and we want to come up with an algorithmic way to come up with a system which you can think of as a program or as a circuit which provably implements the specification. Okay. So, slightly more formally, we are given this formula phi on input variables x and output variables y, and we would like to generate y as functions of x such that the specification holds when you replace y's with these functions. Okay. There's a little catch here that we need to, it could be the case that for some x, maybe there is no y such that phi holds. So we'll say whenever possible. So, written as a logical formula, it means that for every x, as long as there is a y such that phi of xy holds, then phi of x of x should hold. And the implication in the other way is, of course, trivial. If phi of x holds, then certainly there exists a y such that phi of xy holds. So, those familiar with logic, which I believe everybody is over here, would immediately recognize these fx as the Skolem functions. This is the result of Skolemizing a formula with existential quantifiers. In this particular talk, we are going to try to come up with algorithms to generate these functions x, these Skolem functions, and we will restrict ourselves to only Boolean variables in this talk. That's the Boolean functional synthesis problem. And towards the end, I'll mention a few things about what can be done in a more general case, going beyond Booleans.
So, do we ask that for all x, the y should be unique such that phi xy holds, or?
No. I'm just coming to an example. Yeah. In fact, the problem is a bit simpler if y was unique, right? But it doesn't have to be. Yeah. So here's an example which will answer your question. So this is a very simple example: two input variables x1 and x2, one output variable y1, and the specification just says x1 or x2 or y1. This is one possible Skolem function. You just make y1 the negation of x1 or x2. Everything is Boolean. Indeed, x1 or x2 or negation x1 or x2 is of course true always. So it satisfies that thing. Now, in this particular case, it is the case that for every x1 and x2, there is a y1 always, right? But that y1 doesn't have to be unique. So, for example, negation x1 could also serve the purpose. Negation x2 could serve the purpose, or you could just set y1 to true. That will also serve the purpose. Okay? So that's also a Skolem function. So here is a case where for every x there indeed exists a y, but that y is not unique. Okay. But of course, for some combinations of x, y is unique. If you set both x1 and x2 to false, then y1 has to be true. Here is another example which is saying that think of x as a 2n-bit integer, unsigned integer, and y1 and y2 as 2 n-bit unsigned integers. And the specification, written in some formalism, but basically what we're trying to say is that the input is the product of the outputs, not the output is the product of the inputs. The input is the product of the outputs, and none of the outputs should be trivial, which means none of them should be 1. Okay. So if you just, this specification, it's not hard to see at least as a circuit. Yesterday, Shrikant talked about, the difference between formulas and circuits. So at least as a circuit, I should be able to represent this in size O of n squared at most, right? Shouldn't take more than that. And the question is, can I now synthesize y1 and y2 as maybe Boolean circuits that work on x and give me the values of y1 and y2, which satisfies the specification? So I'm really asking for factorization, right? And of course, if I did have efficient solutions for this, I would break crypto systems. So we are not yet there. But this is an example which is not always satisfiable. Not for every value of x, I can find y which satisfies this. In particular, if x is prime, I cannot find y1, y2. None of them are 1, whose product will be x. So this example shows that it can still be interesting to solve the synthesis problem, to find Skolem functions, even when for every x there doesn't exist a y. As long as there are interesting x's for which there exists y, like the product of two primes, and I want to factorize them, it's still interesting, right? And in this case, if x is a product of two primes, which is the interesting case for crypto, then y is almost unique. I mean, you could swap y1 and y2, but it doesn't, right? So you already see that even if it is unique, it's not an easy problem. But if it is not unique, there's this other dimension, that which one of the different Skolem functions. So what happens, I mean, whatever, suppose I'm able to solve this problem and come up with some Skolem functions f. So what happens if we feed x to it? Well, these are functions, they're going to evaluate to some output. And of course, whatever output we come up with, if x is prime, it's not going to satisfy the specification. So, if there is no way to satisfy the specification for a given x, why do we care about what is it generating? So it can generate whatever, but we do care about when for the x there is a y. Okay. So this is the problem setting. I hope everybody is okay with what problem we are trying to solve, right? And we're going to restrict ourselves to the Boolean setting. All right. Now it turns out that there's a nice and long history for this. Of course, perhaps Skolem introduced Skolem functions, Skolemization problem. In the 1920s, and Herbrand also had very interesting work, Herbrand functions, which are kind of the counterpart of Skolem functions in the 1930s. And probably all of us are familiar with Skolem normal form. But all of that treatment and all of that study, it focused on the existence of these forms, not how do we construct these functions. There always exist Skolem functions, but can we construct them effectively? Now, it turns out that some variant of the study goes back even earlier to the days of George Boole, who was considering how do you unify two given Boolean formulas, and Skolem functions can be thought of as one special kind of unifiers. And so, the roots of this problem go even earlier back, almost 200 years. So, why do we want to study this problem? Of course, other than the academic interest in it, it also turns out that there are several applications. So we can do program synthesis, like what I had showed initially. We can, I mean, clearly the Skolem functions are certificates in QBF for the existential variables. This can also be used in planning. Quantifier elimination, of course, we just talked about. Circuit repair can also be used for reactive synthesis. So there's a rich ecosystem of applications, and not surprisingly, people have tried to solve this problem in the past. It's not that we are the first ones trying to do this. So there are several approaches. For example, if it turns out that for all x exists y, phi xy is valid, you can actually extract the Skolem functions from the proof of validity itself very efficiently. But of course, we have seen examples where this formula may not be valid. And so what do we do in those cases? And there are other techniques like iterated function composition, BDD-based techniques, and we'll come to a little bit of that later. BDDs turn out to be special cases of certain nice forms from where synthesis becomes easy. I'm going to talk, really the focus today will be on what's called the knowledge compilation approach, and I'm going to talk about it mostly for the rest of the talk. But there are other guess, check, and repair. I'll spend only a slide on it, which also turns out to be an interesting approach. So there are many different approaches. So how hard is it? So just to sort of make sure we are talking about, we are very clear about how the specification is given and how the functions are going to be generated. We're going to represent everything as negation normal form circuits, Boolean circuits. And it's not surprising that this is NP hard, and one can actually go further in some unpublished work. It's polynomial time solvable if and only if NP/poly is P/poly, right? So, but then the point is, maybe it takes a lot of time to come up with these Skolem functions, but can we get compact functions? And once again, it's not very hard to see that unless the polynomial hierarchy collapses to the second level, we will have specifications for which the Skolem functions will be super polynomial. Doesn't matter how much time you take to come up with these functions. And unless the non-uniform ETH fails, there will be specifications for which Skolem functions will be exponential. So that's kind of bad news, saying that, well, maybe we are never going to get efficient algorithms for Skolem function synthesis. But then there's a silver lining, which is the first one is something like saying that, I mean, this is a hard problem in theory, but can we come up with algorithms that work well in practice? And I'm going to spend only a slide on saying that, yes, there is a paradigm that we and others have worked on, which works fairly well in practice. In fact, it works the best in practice so far. But I'm going to focus more on the second bullet, which is that if the specification phi is provided in some special normal forms, we can provably show that synthesis can be done efficiently. Okay, and so that will be the focus of this talk. So what is this guess check repair paradigm? As I said, there's a long recent line of work. We have done some work along with Akshay, and others have also done. I do not know whether Priyanka is in the audience or not. Probably not. Yeah. So here the idea is that you take the specification, you do some pre-processing, which is I'm going to show you what kind of pre-processing, even when we talk about knowledge compilation, and then you somehow guess candidate functions. And this pre-processing is simple but very effective in practice. And then once you have guessed these candidate functions, you can, come up with a decision question that are these candidates legitimate Skolem functions? And if so, you're done. Otherwise, repair this. So this is where, satisfiability solving, minimum unsatisfiable course and all of that come in. And this guessing, of course, you're free to guess in whatever way you want. So there are two predominant approaches. One is data-driven, which is not the work done in our group. So in our group, we use function approximations, but I really don't want to go beyond that in this slide because that's not the focus of this talk. But this is the general template for guess check repair. So what I want to focus on in this talk is the case for knowledge compilation. We ask the question that, can I take the specification that you give me and can I compile it to a form which allows efficient synthesis? Now, remember, yeah. So repair means that if the check indicated that the quote unquote guessed functions are not Skolem functions, then I have to go and repair them so that they become Skolem functions, and this loop we sort of a time so that we have guarantees on termination of this loop. It's a local repair. Yeah. So we say that, okay, in this part of the input space, it's not behaving properly. Let's fix that. Right. So the question that we are asking now is that, can we compile the specification to a form from which synthesis is provably efficient? And as we have seen that there can be multiple Skolem functions, so we want to compile it to a form from which we can get all of the Skolem functions. It should not restrict our ability to extract any Skolem functions, and it would be good if we can parametrically represent all the Skolem functions from this form. And I'll elaborate more on what I mean by that. So this is the approach that I'm going to talk about, that we take the input, we do some pre-processing, and then we pass it through a compiler, which gives us this normal form, which gives us another form. I mean, semantically the same, but in a different normal form. And after that, there's a polytime engine which can output F. Okay. So the first question is, how do we define such a normal form? And I'm going to introduce what we call the Skolem basis for this. And the second question is, how do we compile to such a form? And I'm going to give a very brief glimpse of how this can be done based on what we call counter-example guided compilation. Okay. All right. So how do I come up with a normal form that from which all the Skolem functions can be obtained? So towards this, we will say that, let that big rectangle represent the set of all assignments of the input variables x, and we'll say a set or collection of Boolean functions on x. So my target is the collection of Boolean functions. So we'll say a set of such functions has a basis denoted by 2 functions on x. If and only if these 2 functions are inconsistent, their satisfying sets don't overlap. So that little boundary in white is to denote that they don't overlap. And a function is in this set if and only if this function is between a and ax or bx. Okay. So basically, I can, in that circle picture, I can say that it has to include this red ax, and it cannot go outside ax or bx. And this thing is still shown in this, slightly whitish thing, saying that, of course, that is excluded because that was the little gap. But B would be in this set F, represented by this basis, right? So this precisely characterizes a certain set of functions. If I give you A and B with these properties, it characterizes a certain set of functions. Now, it's not very hard to see that not every set of functions has a basis. For example, if you take phi and negation phi, then, ax or bx has to be everything, right? And so everything between phi and true will get included in the set F. So not every set of functions has a basis, but interestingly, the set of all Skolem functions for any specification, any Boolean specification you come up with, has a Skolem basis. And moreover, if we are generating the Skolem functions in a specific order, that if there are 3 output variables and if first generating Skolem functions for y1, then for y2, then for y3, then this is actually unique. Skolem basis is unique. Okay. So this is nice, and this actually allows us to now talk about a parametric representation for Skolem functions. So suppose I have a specification phi with just a single output variable, let's say, and I know that all the Skolem functions must be at least as large as this, their set of satisfying assignments, and it cannot be more than A or B. So I can take any Boolean function of x over here and write it out in this form. And for every function h, ax or hx and bx is a Skolem function, and for every Skolem function there is an h such that fx is semantically equivalent to ax or hx and bx. Okay. So now it's just saying find the right hx, whatever suits us, whatever suits our criterion for synthesizing Skolem functions. So, those familiar with logic synthesis would immediately recognize as a case, say, the onset of the Skolem function is A. Whenever A becomes true, the function always has to be true. And the don't care set is B. Whenever B becomes true, I don't really care what the function evaluates to. And in particular, if you choose H smartly enough, you can show that starting from the specification phi xy, phi x1 itself is a Skolem function. It's a function of x, serves as a Skolem function for y. Similarly, negation phi x0, and there's a whole other family of Skolem functions. Anything that you plug in any hx in that, and you're going to get a Skolem function, right? So basically now this whole endeavor now comes to boils down to finding out A's and B's. Given a phi, how do I find out the A and B? Right? So it turns out that for the single output case, which I just showed you, it's actually easy to find out A and B. In particular, A is the set of all assignments for X, for which if I set Y to true, the specification evaluates to true, but if I set Y to 0, the specification evaluates to false, obviously. And B is saying it doesn't matter, whatever the specification evaluates to, whether you set it to 1 or 0, they're the same, right? So I just need 2 copies of this circuit representing phi, and I can get this, right? And of course, there could be shared subcircuits. Now, what happens when I have multiple outputs? So, while we can extend this, in some ways to sort of talk about how to do it for multiple outputs. I mean, what should I be setting for 1 and 0 and all of that? But I guess the easiest way, conceptually easiest way, is to say that let's reduce it to the 1 output case. So let me just quantify out, if I want to do it for the jth output, let me quantify out y1 to yj minus 1. And then once again, it's the same thing, right? So, but of course, the immediate question that it raises is, how am I going to do the quantification? Isn't that where all the complexity now goes and hides? And that's true. And therefore, for the next several slides, I'm going to focus on how do we do this quantification, because once I can do this quantification, it doesn't matter what form phi is. I can get A and B, and once I get A and B, I can get all my Skolem functions, right? So the normal form that we are going to be worried about is going to be a normal form that must facilitate quantification, right? Or quantifier elimination. And so that's what I'm now going to focus on. So given phi as a negation normal form circuit, I want to come up with another circuit which is the result of quantifying out a chosen variable y from the circuit. And so here's a simple example. So this is an SynNNF circuit. The variable that I want to quantify out is denoted in red. And you can see that at the leaves, there is a copy of y, there is a copy of negation y, and there are, I've just represented as a tree over here. So there are duplicated copies of x1 and there's some x2 and all of that. So, the textbook definition of existential quantification for Boolean functions is you take 2 copies of it, set y to 1 in one of them, set y to 0 in the other, and you OR them up. That's what gives you exists y. So all of this is good, but you see that I have doubled the size of the circuit representing exists y phi xy. And if I'm going to do this for multiple variables, this is clearly going to incur an exponential blow up, which kind of is inevitable in the worst case. But I mean, unless some complexity-theoretic conjectures fail. But we'll try to understand what is causing this doubling, and is there a form that will allow us to sort of get away without this doubling. Okay, so can we avoid this doubling is the question that we ask. Now in this particular case, this Boolean function with y set to 1 and y set to 0 that I showed you, in this particular case, it's actually possible to avoid the doubling for a very interesting reason, that when you set it to 1, this whole left-hand side circuit is semantically equivalent to x1. The right-hand side circuit is semantically equivalent to x1 or x2. And since x1 implies x1 or x2, so when I OR them up, I can just say, just take the right circuit. Okay? There's no problem. So this is a case where we say that the variable y is negative unit in phi, which means when you set it to 0, it kind of dominates what would happen if you set it to 1. And of course, if it was positive unit, I would take the output of the left circuit, right? So this is one special case where you don't need to have doubling, right? But I mean, why should we get so lucky every time? So the question is, what if we don't have unit outputs, right? What can we do in such cases? So here is my abstract representation of the circuit. I'm talking about currently just one output variable. So there are some, this is an SynNNF circuit. So there are some y's, some negation y's here, and there are some x's and negation x's here. And it turns out that it's not too difficult to show that if we have this kind of a situation where there is an AND over here with a path coming to y and a path coming to negation y, these are kind of the bad cases which can make representing the result of existentially quantifying out y big in the form of a circuit. So we call this a conflict with respect to y. So basically there is a conjunction inside and two paths, one of which leads to the leaf y, the other leads to the leaf negation y. And this kind of makes it difficult. I mean, in one way you can think of that I was trying to do the existential quantification at the root. If I did not have this kind of a situation for any AND gate inside, I could actually push the existential quantification down, all the way down to the leaves, and that would give me the answer, right? And of course, what is exists y, that's true, and what is exists y negation y, that's also true. I could just set the leaves y and negation y to true, and I would get the result of quantifying it out if I did not have this structure, right? So just to I mean, this was a structural kind of condition. We can go a little bit more and we can say, well, I mean, even if there are such AND gates inside my NNF circuit, maybe everything is still okay. But now to formulate the condition, I have to come up with some kind of a semantic condition. I'll have to say, okay, let me first relabel all the negation y's as y hats, right? So all the negation y's as y hats. And so then I get a function here which is no longer phi, but it has x, y, and y hat in it. But now it is monotone in both y and y hat because it's an NNF circuit, right? And I want to ask that, is there a way to set values over here such that this function starts behaving like y and y hat? And you can see why I renamed it to y hat, because otherwise it will become y and negation y, which is of course false, but it could have become false for other reasons as well, right? Maybe there is an x and negation x here also, right? So, I mean, this renaming just allows me to precisely capture the condition under which you can think of it as I can push the quantifiers down all the way down to the leaves, right? And if there is such an assignment of, then we say that, well, there is a conflict with respect to y, and we say such an assignment is a counterexample to conflict freeness. This assignment shows why this y and y negation y would conflict. If the answer is no, that there is no such assignment pi, then it's called conflict free with respect to y. And this is also we call it in our work that this circuit does not allow you to realize an AND of y and y hat. So it's called AND unrealizable with respect to y. And once this happens, as I just said, you can really push the quantifiers all the way down to the leaves. Just replace the leaves with true, and you get the result of existentially quantifying, right? So if your circuit is a certain form, existential quantification is easy, and it's not very hard to see that DNF, disjunctive normal form, satisfies this property, right? And everything can be converted to disjunctive normal form. So there is no loss of expressive power that I do with this, right? Maybe the circuits will become larger. DNF is certainly not very efficient here. Yeah, so I'm going to talk about, I'm going to come to, it's not polytime, of course, right? So everything will be with respect to an NP oracle, right? Okay. So this first question is that so the first observation is that we can always have a conflict-free circuit. DNF is an extreme case of that, but maybe we can do better than DNF. So towards doing better than DNF, we are going to ask that, well, suppose I detected a conflict in a circuit, can I somehow make use of that assignment that was the witness to the conflict, counterexample to conflict freeness? Can I use that to modify this circuit so that I can get a conflict-free circuit, right? And it turns out that this can be done. Of course, in the worst case, it will result in exponential blowup because, once again, unless some complexity theoretic conjectures fail, we will not be able to existentially quantify out everything in polynomial size. So here is a simple example where, as you can see, that I have a y and a negation y, and this this circuit has a conflict with respect to y, because if I just set everything else to 0, if x1, x2, x3 and x4 are all set to 0, then this becomes a 0, this becomes a 0, this becomes a 0, so you get y and y bar, or y and negation y at the top, right? So y and y hat at the top. So and that's the assignment on x1 and x2s is a witness to that. It's a counterexample to conflict freeness. Okay. So the question is that once I know this counterexample to conflict freeness, which is the assignment to x1, x2, x3, x4, it's not very hard to see that I can just take this, flip it around, and basically conjunct the original circuit with this, and this is going to be semantically equivalent to whatever was being represented by the original circuit, and it has strictly fewer counterexamples to conflict freeness. So this says that, well, if I could find out each of these counterexamples, and if I right, I mean, why is this? Why does this work? Because remember, in the previous case, we saw that when I set this assignment at the leaves, the output becomes y and y hat, which means that in the original circuit, if I had put negation y over here, the output have become false. So for this assignment to the x's, the output becomes false regardless of the value of y. Okay, and I'm just allowing this to happen through this now, right? Whenever this is true, this side will automatically become false. So it will conjunct over here and give it false. And in all other cases, we have preserved whatever the circuit was doing, right? And this new circuit does not have this counterexample to conflict freeness, because whenever you give this, the output cannot evaluate to y and y hat, because this part will come and mask it out, right? So it is strictly fewer counterexamples to conflict freeness, and one can do this, finding out one counterexample at a time and keep adding those things, but then that's not going to be probably very smart. Yeah, so they said this is no longer a counterexample to conflict freeness, but then we can do slightly better than this. We can come up with what are called generalized counterexamples. So for example, this is a circuit that I can put here, and we have come up with some ways to come up with the circuit. Once again, in the worst case, this can be exponentially large. So this can block off a whole bunch of counterexamples at the same time. Okay. So one doesn't need to do it counterexample at a time, but worst case, of course, this can blow up exponentially. All right. So just to sort of recap what we said that, well, if there is if I disallow these conjunctions with path to y and negation y in my circuit, then we are doing good. And we generalized it to something which I can check semantically at the root of the circuit. So this kind of circuit structures where there is no and with paths coming down to a literal and its negation, this is what's called a weak decomposable negation normal form. It generalizes something called a decomposable negation normal form, which is very well studied in the literature, particularly in the knowledge representation community. But we don't need something as strict as this. We can just go with what I showed here. And this is sufficient to do quantification, which means after that everything is easy. This is sufficient to do polynomial time synthesis. And what I just showed you through the examples is that we can generalize it a little bit more. We can talk about whether at the root I'm getting something like y and y hat. I showed it for one output. So in the multi-output case, what happens is you can group, y1 and whatever, y1 bar, yk and yk bar. And if I'm trying to check whether everything is okay with respect to yk and yk bar, what I have to do is I have to set everything prior to that to 1, and I have to ask for an assignment here which makes it yk and yk bar. Why am I setting these to 1? Because I'm effectively quantifying these out. Remember, we said that, so if I first check it with respect to y1 and it's okay with respect to y1, then I can set y1 and y1 bar to 1 and effectively quantify it out, then go to y2. And if I do it in this order for all possible y's, then I can actually quantify out the y's in that order, okay, without any blow up. So this is also sufficient. Once I'm able to do the quantification, after that I can get the Skolem basis, and then I can get all the Skolem functions. And here is a simple example to show that it is order dependent. Something. So by the way, this thing is called a synthesis negation normal form. I think it's getting hidden here, but SynNNF. Okay, yeah. And here is a little example. So in this example, what you see is that there are two outputs, y1 and y2. And per se, if you look at it, y1, of course, doesn't have a negation y1. So there's no way you can get a y1 and negation y1, but y2 can give a y2 and negation y2. So this is not in weak DNNF. For example, there is indeed a path to y2 and negation y2. But then if I say that, well, is there any way for me to get y1 and y1 bar at the root? There is no way, there is no negation y1 here. So I can set it to 1. And now I ask, is there a way to get y2 and negation y2 or y2 and y2 bar at the root? But because I've set it to 1, there is actually no way to get y2 and y2 bar. So this is therefore in SynNNF with respect to this ordering. And this order matters because in this particular case, if you flip the order and if you do y2 before y1, then you actually can get y2 and y2 bar over here. So this is not in SynNNF with respect to the order y2, y1, but it is in SynNNF with respect to the order y1, y2. And but as long as synthesis is concerned, it doesn't matter. As long as with respect to some order it's in SynNNF, we can synthesize all of the Skolem functions. Okay, so a natural question to ask here is that, well, I mean, how does this compare with respect to other forms that are already known? And so reduced ordered binary decision diagrams, I believe several of you already know here. This is a very well-known data structure for representing Boolean functions. Of course, exponential in the worst case, exponential size in the worst case. And then these have been studied in the literature. I talked about decomposable negation normal form, the weak decomposable negation normal form. There's also something called deterministic decomposable negation normal form. And these have been studied very well in the literature. And it's actually not very hard to see that, to show that once you know these definitions, that these are strict inclusions, right? That every ROBDD is a deterministic decomposable negation normal form. I'm not going into the definitions of those other things. I'm just trying to focus on this synthesis negation normal form, which is what is really needed for synthesis. But if you have it in any of these other things, then of course they're also in synthesis negation normal form. So synthesis becomes easy. So if your specification is given as a BDD, for example, synthesis is very easy, polynomial type from there. And then, by going to this more general form, are we gaining in terms of succinctness? Are there things that we can express more succinctly here as compared to other things? So here there are some unconditional results. I mean, we know DNNF is exponentially more succinct than ROBDDs, and SynNNF strictly generalizes DNNF. So this is also exponentially more succinct than ROBDDs. The other succinctness results are conditional. If well-regarded complexity-theoretic conjectures are true, then SynNNF is indeed more succinct than the other forms that we have, right? Okay. So this was nice, but if you go back and look at this, here we said that this was a sufficient condition for doing polynomial time synthesis, right? So now we want to ask, well, is there also a similar necessary condition which would sort of precisely characterize, right? And that's the question that we asked next, that is there a necessary and sufficient condition? So essentially what, I'm sorry, it should be Boolean, not Boolean, I don't know. I thought I corrected that typo, but it didn't show up. So we are asking that, is there a normal form of this circuit representation of Boolean functions such that whenever you give me a specification in that form, and of course that form has to be universal, I should be able to express any function, any specification, any Boolean formula in that. And whenever you give me something in that form, Boolean functional synthesis is polytime. And not only that, if there was another class of circuits which admitted polynomial time Boolean functional synthesis, then it should be possible to compile from that class to this new class in polytime. And if there was another class of circuits which admitted polynomial sized synthesis, doesn't matter how much time it took, then it should be possible to compile that class to C star also with a polynomial flow. This is the question that we are asking, because if we answered this question, then we would know that at least this, I mean, of course, this doesn't mean that this class C star has to be unique. There could be multiple such classes, right? Or there could be multiple such normal forms. And you note that when I'm talking about class of circuits and normal forms in slightly interchangeable way. This is not necessarily a syntactic class, it's not a structural class, because the synthesis negation normal form, as we defined, has a semantic check in it. But we're asking, is there even such a form? Does that anything that would admit efficient synthesis can be efficiently compiled to this form? No, but it also has to be universal. Every Boolean function has to be expressible in this class. Universe, yeah. I mean that is the the basic requirement. Otherwise, right? And so it turns out that yes, there indeed exists such a class, and I guess the name SAUNF is appealing to people from Southeast Asia. So this is what is called subset and unrealizable normal form. I'm going to show what this means in one slide, but even if you don't completely follow what I'm going to show in that slide, it's fine. It's just to say that yes, there exists such a class, and the checks there are not any more complex than the checks that we showed for synthesis negation normal form. So what is this class? So it's somewhat similar, but now what I'm going to do is that I'm going to say that, well, remember, this was our SynNNF circuit, and these were the output variables and their negations. And notice that here I have kind of put some yk over here and also yk over here, some negation yk over here and negation yk over here. So I'm going to linearly, I'm going to partition the leaves labeled by the outputs and their negations, and I'm going to come up with a linear ordering among those partitions. And it's perfectly okay to have this, so essentially this is a circuit, this is a DAG, but you can think of it at the last level, I'm not allowing sharing of leaves, okay? So everything above that is all the same, but at the last level, I don't allow sharing of leaves. And so I can get multiple copies of the same variable over here, and I want to group these and I want to order these groups. I want to partition them and I want to order them. So the same output variable can get split into two different partitions. This gets split into two different partitions, and they could be ordered interspersed with other things. So SynNNF was a special case of this where everything was grouped together. All the YKs were grouped together. All Y1s were together. All negation Y1s were together. So this says that can we break it up into these subsets and order them? And then we do something pretty much similar. We say, okay, I'm going to pick one of these over here, set everything to the left of it to ones, and I'm going to look at, whatever the YK bars that appear to the right of this, not to the left of this, and all other YKs that appear to the right are zeros. And, you might ask why zeros here? I mean, kind of these are already dealt with. So these are not yet dealt with, but then, the technical proof is long, but so this is a kind of check that I want to do, which is very similar to the check that we had earlier. I'm just trying to check if the circuit evaluates to some Yk and Yk bar. It's just that the way I'm going to initialize some of these variables are different, and then the rest of it is just a NP Oracle query. Yeah.
YK is appearing on the left and also in the gray one. So
yeah.
If I'm setting it to one, that means I'm setting it to one in the gray area too.
No. So that's what this Yk appears at multiple places, and I have to do this check for each of these groups. And when I come to this group, the check for this group has been done. So whatever has, this is kind of like generalizing what we did earlier, right? Earlier it was with respect to individual variables, all copies of the variables were grouped together. But here I'm talking with respect to partitions of instances of those variables at the leaves. So everything that has, so I'll start from here, I'll do the check here. If it passes, I'll go to the next one, I'll go to the next one, and so on. And whatever is done, I can just set them to 1. Whatever is not yet done but has the same leaf, I have to set them to 0, because of whatever. That's what makes the proof go through. But you look at it, the check is pretty much very similar. It's you set some things to some constants, and then it's an, co-NP query. All right. So, and this turns out to be necessary and sufficient. This is the class such that if there was any other class of circuits which allowed polynomial time synthesis, it can be compiled to this class in polynomial time. And I'm going to actually show you the rough scheme for this, how to do this. And if it can be compiled to polynomial side Skolem functions, then that can be compiled to this class with a polynomial blow-up. Okay. So how does this compare with other normal forms? Of course, this generalizes SynNNF, as you can very well see. SynNNF is a special case of this. And so everything that SynNNF subsumed is also subsumed here. Some of these, very well-known, like BDDs, can be compiled in linear time to SAUNF. It is strictly more succinct. I mean, we have examples where, this is strictly more succinct. And of course, these results follow from the SynNNF succinctness results. So okay, this looks like a nice, normal form in which to work with as far as synthesis is concerned. That allows us to quantify the variables, which allows us to generate the Skolem basis, which allows us to generate all possible Skolem functions. So can I build up this thing compositionally? If I have 2 circuits in this form, can I combine them to get another circuit in this form? That would be really nice. So disjunction is very easy. You can just take 2 things, put a disjunction at the top, and just goes through. Conjunction is easy if, the every pair of Y-labeled leaves of phi1 and phi2 are consistent in the sense that they don't go and meet up at an AND gate somewhere for the first time. They are already sort of taken care of within. Right? It should not be that there is a Y which comes from phi1 and there is a negation Y which comes from phi2, and the first time they meet up is at this new conjunction. As long as I've taken care of that they can't show up at the top in these individual ones, then it's okay to do that. So under some conditions it can be done constant time, but yeah. But otherwise, once again, conditional results that it's not possible unless some other things fail. Existentially quantifying, of course, that's the whole point. That's why we did all of this. But if you say, no, I just want to quantify y3, y7, and y9, that is not possible in linear time in general. But if you say, I want to quantify y1, y2, y3, which is as per the order that we ordered these subsets, then that can be done. So ordered quantification can be done. Checking if it is in this form, if I give you the linearly ordered partition, then it's of course going to be complete. But if I don't give you this, then you have to guess it and then check it. So, I mean, there's a gap. We know it is going to be hard in since sigma 2, but yeah, I mean, probably this gap can be closed. Yeah. All right. So how do we compile? Yeah, so we are almost towards the end of my talk. So how do we compile circuit classes which admit efficient synthesis to this SAUNF? It turns out that there's a very simple recipe to do this. So suppose I start off with, some class of circuits which admits efficient synthesis. So what I'm going to do is I'm going to say, well, since it admits efficient synthesis, let me feed it to the synthesis algorithm for that class, right? And it will give me some Skolem functions, right? Because that's the class that admitted efficient synthesis. And now I can take these Skolem functions and construct a new formula which looks something like this. It says the original formula disjuncted with y is equivalent to the Skolem function, conjuncted with this thing, right? I mean, this looks strange, but if you think about it, this is the original formula with the Skolem function substituted for y. So this is actually exists y, right? And this is really saying I have set all the y's to whatever Skolem functions I've got, right? Now, this conjuncted with exists y is, I mean, phi xy certainly implies exists y, and this also implies exists y, right? Because this is a Skolem function. So whenever this holds true, we know that exists y will hold true, and whenever this holds true, this also holds true because quantification only weakens. So this whole thing is weaker than this. Sorry, this thing is weaker than this. So when I conjunct them, I actually get this back, right? And this doesn't add any more to, I mean, this is actually stronger than this because this is a Skolem function over here. So whenever y that is equivalent to fx, phi of xy will hold true, right? That's from the definition of Skolem functions. So this whole thing becomes semantically equivalent to phi xy. That's what we wanted. But then because of the way we have, so the partition here should be such that we first have to take this set of y's, then we have to take this set of y's in our SAUNF ordering. And this is where we needed to split the y's into two parts and consider them. And then we can show that this actually gives SAUNF. So this is semantically equivalent to this, but once I have obtained the Skolem function, I can convert. So actually, this also tells something very interesting that if you give me one Skolem function, I can get the SAUNF thing because it doesn't matter how I got f. And once I get the SAUNF thing, I can generate all Skolem functions through the Skolem basis. So I just need to know one Skolem function to be able to generate all the Skolem functions. Okay, so to summarize, I think I mentioned that this problem has a lot of applications. There's a long history of work. I very briefly talked about guess, check, and repair and tried to delve a little bit more into knowledge representation. And interestingly, all of these are also reasonably practical. In fact, we have implementations of these which we have run on benchmarks, and our tool and the tools of other groups, this seems to be increasing the number of benchmarks that we are able to solve. And advances are dependent on both theory and practice shaking hands, but we are still missing a satisfactory explanation of why a large class of problems are easily solved. We know that once it is in SAUNF, it can be easily solved, or once it's in SynNNF, it's easily solved. But it doesn't look like that a large class of the examples are in either of these forms. So there is something more hiding there. Of course, we know that whatever can be easily solved can be compiled to SAUNF, but a more satisfactory explanation of what causes this problem to be easy is still elusive. Where do we go from here? To really figure out whether this is useful in practice, we need more benchmarks. We can talk, since we are now able to talk about all Skolem functions, we have characterized them, we can pick and choose from there. Maybe something is more preferred than other. And then, of course, we can go beyond propositional logic. And in 22, Akshay and I, we took a first step in this direction and we showed that, well, if you go to first order logic, most Skolem functions are actually not even computable. But there are certain fragments which are well characterized, and we came up with a characterization of exactly when is it computable. And then there is some ongoing work that we are trying to do knowledge compilation for Prisberger for polynomial constraints over reals rationals. Thank you.
One quick question.
Yeah.
Some of these forms, the SynNNF, for instance, is more exponentially more succinct than BDDs and some others. But some other separations were conditional. Is there a reason why these should be conditional, or because it feels like this kind of thing should be known unconditionally, right?
Well, yeah, we haven't been able to prove the unconditional succinctness.
Yeah. Okay.
But if we, so for example, if you're asking where do these conditions figure in the succinctness proofs, is that the question? Why do we even have to?
No, I guess my question was: is there would we be solving some complexity-theoretic problem if we were to have unconditional separations in those cases?
Yes.
Exactly.
Okay.
Thanks.
Oh, this is published. Where was it? Yeah. So if we could get SynNNF, this is a one-way implication, right? If P is not equal to NP, then we can show that SynNNF is, there exist formulas in WDNNF which are super polynomially larger than the SynNNF formula. Right. There is,
Right.
At least we don't know. Yeah, maybe there is.
So maybe let's take the rest on coffee break. Already we're going to have a slightly shorter coffee break, but maybe not 15 minutes. Shall we start 5 minutes late the next session? So let's keep 20 minutes. Okay, so Pradeep suggests that we absorb the delay in the lunch break. So if that's okay with you, with everyone, we'll start 15 minutes late. So we'll have the full half an hour for coffee. That's where we all. 10:45, but let's start sharp. Yeah. Thanks everyone.